Hello, everyone. It's good to see you all again, and happy Friday. Very happy to be able to have a chance to maybe talk about a bit of math to end this week. Sorry I was a little bit late. I was actually on the phone with MIT. As some of you know, there are many people around the world right now who are trying their best to try to stop COVID-19. And so after, as some of you know, I made an app that will help to track whether or not other people nearby have COVID-19. And actually, after this release, a lot of people started to want to talk, whether they be from one place or another. And so I was busy on that. But in any case, yes, Novid, that's what it's called. So in any case, one has to also talk about math, and I'm very happy to have this chance every single day at 4 o'clock to be able to talk to people about math. Of course, I say 4 o'clock because I happen to live in Pittsburgh, Pennsylvania, and that's the time that it is right now over here. Now, if you're new to this daily live stream, just as a reminder, sorry, that wouldn't be a reminder. If you're new, it's not a reminder. But if you're new to this daily live stream, the way that this works is it's going to be very different from a normal math class because the questions are not going to come from me, they're going to come from you. And in fact, I love to have this opportunity to go and see what kinds of things people are interested in. And then I'll choose to answer the questions based on that. If you have been here before, I can tell because you usually post into the chat that you want to see the green shirt. Now, my goal, of course, is to make it so that it's not that everyone here is only people who have been here before. I would love to always keep welcoming in new people. And so, if you end up liking what you see, please tell others. Now, I know from experience that most of the topics that we will be talking about will be somewhere between Algebra 1 and Geometry. Although, they usually are not the kinds of things you'll see in your class, because I trust that your teacher will already have taught that to you pretty well. So instead what I'll do is I'll be taking complicated topics or weird questions that people ask and trying to translate those into ideas that I might think of that will have something to do with algebra or geometry. Why don't we get started? What kind of questions are here? Let's see. Jason Zhang is asking, how close are we to convincing Google to put this app out? To be perfectly honest, we're not done with that yet. In fact, we still haven't made progress. If any of you know anyone at Google or anyone who knows anyone at a medical institution who wants to help make the COVID-19 be able to be tracked, I would love to connect afterwards. But let's see, what else can we do here? We can talk about math. That's actually the goal of this particular live stream. So I'm looking at all of these different questions. I mean, I see that somebody has brought up Pythagorean theorem. That's a common thing. Whenever there's a way I can tell you there's a way to see it, if you just go to the Daily Challenge website, there's a completely free explanation of the Pythagorean theorem, which is something that you might not expect. So I recommend you go there if you're interested in the Pythagorean theorem. That's our normal website, not the live stream. Other questions? Let's see. I'm trying to think because I see an interesting one. Ava Joe asked, what's your favorite math riddle? So if I wanted to have a math riddle, okay, I'll say this. It's not actually the hardest math riddle in the world, but it's one of these things that was also related to someone saying they would like me to talk about a system of linear equations, talking about solving linear equations. So one of the favorite tricks that I ever learned when I was doing math contests when I was young was this thing of saying, hey, let's suppose that there are 3 people and they're all playing basketball. Like somehow 3 people are playing basketball. Maybe they're called Alice, Bob, and Charlie or something, right? And then you want to kind of figure out how many points each of those people got. Now, this particular riddle is actually one that I covered in the Daily Challenge course, and it also happens to be one of the top it was a winning YouTube video in what's called the Math Video Challenge that the Math Counts national competition put up. But the question is roughly like, if you know that A and B, Alice and Bob together got so many points, and then B and C together got so many points, and A and C together got so many points, well then how many points did they get all together? That's maybe one of my favorite ones that's actually a math problem. Although, again, because that's already covered elsewhere, I won't do that here. If I was to think about other kinds of like math paradoxes or some math thing that I might think is interesting, I think here's one that actually is quite a funny one. I mean, this is the favorite one that I like to answer to a lot of people. It's that a lot of people ask, what is 0.999999 and so on forever? This is somehow a lot of people ask me this question. Does anyone know what is 0.999999999 altogether? I'll keep on, if it keeps on going. 1. Somebody says this is 1. But the question that a lot of people ask is it really 1? Or is it just like almost 1? So is it like exactly 1? Or is it just like really, really, really close to 1? You see, that's an interesting question. And the answer is, it depends. It depends. It depends about whether or not you understand what the ... means. And so, yes, people are saying, yes, it's really 1. So it seems like some of the people here in this live stream have been thinking about this sort of thing. And the reason why it is actually exactly 1 is because on the left side here, what we drew is we just drew a representation of something. We just drew like our impression of what something is. We're saying we've got a number, and the way I'll describe the number is 0.9999 ... And the point is, what that means. What that means is, whenever you write something with ... the meaning is, if it gets closer and closer to some number, what is it? So this is the number you approach. So when you write the ... you actually are referring to the number you approach if you just wrote more and more and more 9s. So it's not even an issue of whether you actually approach the 1. The ... already means whatever you do approach. And how do I know that you actually approach 1? It's because I just have to look at the distance away I am from 1. So for example, if I only have one of the 0.9s, how far am I from 1? Can anyone tell me what is 1 minus 0.9? What's this? 1 minus 0.9 is 0.1. Good. So this is this 0.1. And that's fine. But what if I had 2 9s? What if I had 1 minus, what is this? 0.99. Does anyone know what is 1 minus 0.99? So that now there are 2 9s instead of 1. Well, of course, 0.01. And now what you should see, and I see a lot of people are answering, which is great. What you see here is that if I just write more 9s, what's going to happen? I get a number, I get a difference, which is closer and closer to 0. So the key is that as I keep going and going and going, and adding more 9s, look at how far away I am from 1. The distance I am from 1 is going to 0. And because the distance I am from 1 is actually going towards 0 and getting closer and closer to 0, I mean, in some way that however close you want to be to 0, you eventually get there, then we actually say that this equals 1. This is just another way of writing 1. So that's maybe one of these things that a lot of people ask me, and I find that if you ever find someone asking you, does it really get to 1? The best answer is, that's just a way of writing down a meaning. The ... just means whatever it gets close to, if it gets close to something. And the answer is 1. Okay, more questions. What else do we have? Can you say a math joke? Says David Zhao. A math joke. I mean, I'll say I like this one. I saw this one. Just a second. Let me save this. So I saw this like this fun T-shirt. How did it go? The T-shirt looked like this. Has anyone ever seen a T-shirt that says this? So this is a shirt that I think I saw some people wearing this around. The pie and I joke, yes, that's another joke, but we already talked about that in this live stream. So I ate some pie. Exactly, that's what this is. So you know the square root of -1, that's I. So that's an imaginary number. You cannot take the square root of -1 and get a normal real number that would measure a length, like positive or negative. 8, well, that's just 8. I'm sorry, I spelled 8 wrong, but I feel like writing it that way. Okay, now this funny symbol, this thing that looks like a E that's sideways, it's not an E. In fact, does anyone know, it's a Greek letter, this little squiggly thing that looks like an E. Does anyone know what that is actually in Greek? Whoa, that's weird. This is a Greek letter, yes, it's sigma, capital S, sigma. So you use the sigma whenever you are doing more advanced math to represent adding up lots and lots of things. Actually, let me talk a little bit about the sigma. Like sometimes in life, you might see, if you're doing math, you might see something that looks like this. Sigma k equals 5 to 10 of k squared. And I'm just going to tell you how to read this, okay? Again, I didn't learn how to read this until quite a bit later in life, and I always thought it looked mysterious. I thought it looked like something hard. It's not. It's actually very similar to what we call a for loop if you do programming. A sigma is just a for loop. All this means is that I'm going to take my k and let my k go from 5 to 10, counting up one at a time, okay? But as it's counting up one at a time, I'll go and calculate the k squared. So when k equals 5, 5 squared is 5 squared. Then the k counts up 1 to 6. And I write 6 squared because I see a k squared. So it's like when k equals 6, it should be 6 squared. Then at some point k is going to be 7, which is 7 squared. Then at some point k is going to be 8, and that's 8 squared. And then I'll have k equals 9, which is 9 squared. And then I have k equals 10, which is 10 squared. So this sigma notation is just a very easy way, a more compressed way of writing down this very long sum. Okay, but I just called it a sum, you see. This is a sum. And the reason why, does anyone know the reason why they use the sigma to represent this? Is there a reason why you might use the Greek letter sigma to represent adding up all of these things? You know, like there are lots of Greek letters. I could, for example, have decided that instead of using sigma, maybe I should use a different Greek letter like pi or something, right? But why sigma? Sigma because it's an S, and S is the first letter of the word sum. So the idea of that sum, this is a summation notation. And so we actually would write that this is sum. Sum. Okay, that's what this is for. And that's exactly why we use the sigma here. Oh yeah, okay, pi is just this pi, right? So it's like I ate some pie. Okay, looks like I shouldn't write ATE here. I should actually, oh no, what happened? Okay, let's get rid of that thing there, right? We should write EIGHT. So really the way to think of this is I ate some pie, and that's the joke. And sometimes there's a picture of a little piece of a pie underneath. Sometimes it's a picture of a plate with crumbs from pie underneath. Same principle, right? But somebody asked, yes, thank you. What about product? You know, like, what if I didn't want to do the sum of k squareds? What if I was curious about something else? What if I felt like, you know, I'm going to write it over here since I need some more space. What if I wanted a nice way to write this product? I want to take 5 squared times 6 squared times 7 squared times 8 squared times 9 squared times 10 squared. Well, it's still going to be something with k equals 5 to 10 of k squared. But which Greek letter should I put in that spot that looks like a ghost? Right. So the sum was sigma, which is the S, right? And so the Greek letter for S was this sigma, so we wrote a sum. Product, the product is a pi. So in fact, this is actually what you write. You write a capital pi. This is not the lowercase pi, this is the capital pi. And so now you've also seen what this product notation is. In fact, later on, you might sometimes see in a math book this weird big pi. When I first saw that, I was actually scared. I was like, what the heck is this? Why is there a big capital pi? And then at some point, someone said, all that means is you multiply it. Pi notation, asked Grace Yan. It's like product notation. You could call it pi notation because some people call this sigma notation. So I guess this is pi notation, right? And so, yeah, you're allowed to do this too. It's just, it turns out there aren't many other things you do. It's very rare that you do like minus notation. I don't even know what that would mean to say I will always like subtract or not. Like if I did a minus notation, I could probably do it with a sigma notation too. I'm going to tell you one more cool thing. The other cool thing is that I don't know if anyone's ever seen a symbol that looks something like this. Has anyone ever seen that? You don't have to know what that means, by the way. You just have to have, I'm just asking, have you ever seen that written anywhere? That's called an integral. That's called the area under something. That's also like sums. It's actually when you are trying to find the area under something, you can break it into little pieces and add up all of the areas. So does anyone know why that symbol is written there? Does anyone know why, if this is supposed to mean the area under something, meaning I'm going to add up lots of little pieces, why in the world should I write that symbol? Who invented that symbol anyway? It was clearly somebody who likes to play the violin. Well, I'm not sure if that's true or not. But why would that, what kind of symbol is that anyway? What is that? Why would anyone write that? Well, it's like a sum. This is sort of like adding up lots and lots of things. You're adding up lots of little shreds to get a big area. So that is also an S. It's an S for a sum. So actually all of these things, like this big E, which is not an E, it's a sigma, that's sigma for sum. This thing, which is also for getting sums, this is actually an S. And over here, this products. If you want products, go use a capital Pi. Okay, so that was a long answer to your question of maybe what's my favorite, what's a math joke? Tell you guys a math joke. This guy's kind of fun. Okay, what other questions can we get here? Oh, violin showed up. Very nice. And somehow violins have these little marks inside. I think it helps to make the sound. Maybe it makes this thing resonate better. I'm not really sure. I actually don't know. I never played violin, so I don't really understand how the violin's sound chamber works. I only know the basic physics of like a string has a wave and so it vibrates. Okay. And Joe, this is too complicated for your tiny brain. Absolutely not. This is not too complicated for you, and your brain's not tiny either. So the bottom line is like, in this particular live stream, what I really try to do is, yes, we'll talk about some things which are things that you might have seen before, like, maybe adding up some stuff. But my goal here is also to kind of give you some mathematical culture, to show you a little bit of what you might see later, and to explain things that I myself didn't know until much, much later when someone said, that's a sigma, not an E. I thought it was an E for the longest time. Okay. More questions. What do we have here? Aha. Looking at all of these things. Okay, Daniel Chu says, isn't there a thing that you can make infinite chocolates if you cut it in a certain way? I'm not sure what you're referring to, but I'm going to say that it's a little bit difficult to make infinite chocolates because chocolate is a real thing. It's made of matter. It's made of atoms. And as some of you may know, if you've taken chemistry, if you cut and you cut and you cut, at some point, the only thing that you have left is an atom. Like you could even take a molecule of sugar. What's that? I already sort of forgot. Is sugar like C6? There's some C's and H's and O's. What is sugar? Is there like a C, there's an H, there's an O, C6? I think it was this. It's been ages since I did any of this stuff, but like I think that's sugar. It's like, so you go and cut, and at some point you got this thing, and you go cut the sugar molecule in parts, and at some point all you got left is like the carbon, right? You go and cut, and at some point you can't cut forever. So I'm not really sure you can get infinite chocolates. So that's what I'd say here. Other questions? Time WW Brody asks, do you play poker? Unfortunately not. I think I sort of knew the rules, but I would be really lousy at playing poker. Oh, actually, you know what? Even if you don't know the rules, you can probably still play poker. You'll just probably lose. In the sense that people will say, go and like pick a card or something, and you'll pick a card. So in theory, I guess I know how to play poker, except that I've been around people who are far, far better at that than me. So I guess I didn't dare to try, because something about poker is it costs money if you lose. Sometimes, depending on who you play with. I prefer to play games that it doesn't cost me money if I lose, so I didn't get into that. But I know there's tons of people who are like really, really into poker and also very good at it. More questions. Oh, this is really interesting. So, yeah. So Da Kui Queen 5000 says, why is math either too hard or too easy? I think what that means is that what you should do is, if it's too easy, go find questions that are harder, and if it's too hard, go find questions that are easier. The best way I've found to do this is to go and look at math contest questions. That's actually why, like for the classes that I run, I choose all of my questions to be of the type that you might find in a math contest. I find that if you are doing questions that are maybe more like the school textbooks, those are much more likely to be too easy. And if you go find some hard contests, they'll be too hard. But what you need to do is you need to go and say, all right, maybe I shouldn't do all these hard contest questions. I should go and find a hard contest and do the easier questions at the beginning of it. And at that point, those will be just right. So I think that it's really, really good that you're already thinking about questions being too easy or too hard. A lot of times, people only think of questions being too hard. And if you only think of questions being too hard, you may accidentally just do questions that are too easy. but that's not productive. It's much better to make sure that you're always going to work on questions that are actually not too easy and not too hard. And that's the goal. Okay, what else can we do here? Well, here's what I'm going to do. Because I haven't gotten as much sleep lately, I'm going to try to zoom in so I can see your comments more clearly. So let's do this. Zoom. So this is on my screen so that I can see what everyone's comments are, because I like to be able to see immediately what you guys are saying. It's actually quite entertaining. So what do I have here? Oh, David Xiang asks, do you have an AOPS account? Well, yes, of course I do. But I'll tell you when I made the AOPS account. AOPS is this website that many people go on to go and find old problems, and also those are free. Old problems are free. And I actually also used that because about 10 years ago, I was helping Carnegie Mellon University reach out to lots and lots of great potential students. And so the first time I made an AOPS account, I think was something around there. I was like using it to go and talk to people about Carnegie Mellon. Actually, if you want to see what my AOPS account has done, what you should do is you should go and search online for what's called the Carnegie Mellon Math Jam. And you can find out like what I and a few of my other professors, colleagues, other professors here at Carnegie Mellon were saying when people were asking questions about Carnegie Mellon University. But yes, I do have an AOPS account. It's PSLOH. That's the real one. All these other people who made their AOPS account called Po-Shen Loh, or like the real Po-Shen Loh, or like Po-Shen Loh, where you spelled it like a magic potion, or like lotion, whatever. Those are not actually me. Those are not actually me. So my real account is this PSLOH. More questions. Oh my goodness. Pi says, what did you do in your free time outside of teaching before coronavirus crisis? That's a really, really good question, right? So you guys know what I do in my free time now is basically find a way to get every single person back to work again or back to school again. We can't survive like this. We have to stop this. I'm using all of my time right now to go and solve this. Before this, what was I doing? Actually, outside of teaching, I love teaching. I was doing a lot of work. You're asking a question, I'll give you an honest answer. I was doing a lot of work actually to make our online classes. So actually you're watching all of these like free YouTube Daily Live because we already built the whole studio. Oh, I'm pointing at this, you can't tell, it's just a green screen, right? But I mean, we'd built an entire studio. So I was actually using all of my free time to record classes, like a system of classes that goes all the way through middle school competition math. So that's what I used to be doing. And in fact, some of you who studied with me know that I was supposed to go and make a course on probability. And in fact, we will still make the course on probability. The only problem is that COVID-19 came. And then at that point I said, look, if I know something that could help to stop this, I'm going to maybe put aside making those classes for now and try to find a way for people to get back to school and get back to work. Okay, more questions. Missing dollar riddle. I'm not sure what that means. So to be honest, I actually don't know what all of these riddles are by name. If you talk about a missing dollar riddle, could I make up a riddle about this? It almost sounds like one of those magic tricks where somebody puts a dollar in and it disappears. But I'll tell you something about dollars. This is a fun thing that I learned when I was in college, okay? So as you can see, if you ask me a question, if I don't know how to answer, I'll just use it as an inspiration to give you something else that's kind of fun. So this thing is something that you must please promise not to do this at school. You might get in big trouble if you do this at school. Actually, I should probably not tell you that. Well, okay, just as like, please promise don't do this at school, okay? So somehow, like, I'm going to tell you something very, very dangerous. It's called a dollar auction. Okay? And the way this works, maybe some of you have heard of this thing before, right? So the way it works is I hold up a dollar bill, all right? And what I say is, hang on. So let me try to get this straight. So it's like when you have an auction, everyone can go and say how much are they willing to pay for that dollar, okay? Yes. Wait a second. So let me try to get this straight. There's going to be something that goes on here where it's like, wait a second. So now I'm actually trying to get this straight. And while I'm trying to get this straight, it's quite possible that someone in the chat is also going to be able to give us the statement of it. Because what I really want to do is I want to analyze it. It's a situation where people are bidding, all right? And people say, okay, I'm willing to pay 10 cents for your dollar bill. Or I'm willing to pay, and then you go and find out who's willing to pay the most for the dollar bill. But how does this work exactly? So it's like somehow when they are willing to pay $1, if they're willing to pay like 10 cents, who wins the auction is, I think, is it the winner? Wait a second. Yeah, I think the way it works is that the winner wins, and the second high, just a second. So I'm actually afraid. I don't remember this one off the top of my head. I remember that this is a game theory thing for which, oh yes, thank you, somebody has put this. So you bid for $1, and the highest bidder gets the $1, and the second highest bidder pays their bid. So that's what I was thinking in my head, but I was like, that doesn't sound quite right. But let's do that one, okay? So that's the one that I thought of, and I was like, but that sounds dumb. But okay, let's do that one anyway, all right? And the rule is that somehow, yes, so they're gonna bid, and you can say, I'm willing to pay 10 cents. And someone says, I'm willing to pay 50 cents. And the deal is that somehow the person who has the highest bid wins the $1. And the second highest bid pays. So that sounds, I'll tell you, like, maybe it's just because I've thought about this too much, but like, if you look at this, what usually will happen? So somebody will be like, okay, you could get $1. And I think it should be a little bit more complicated than this, to be honest, to make it something that you'd even want to play in the first place. But it's like the moment, actually I do get it. Okay, I can solve the game theory here, okay? So it's very simple. There's a prize, it's called $1. And you go and bid, and the highest person will actually get the $1, and the second highest person is going to have to pay for it. Actually, this is a really very interesting game. So what would happen? What would you do if you're in a room and nobody is bidding anything? What would you do? It's like, well, if nobody's bidding anything, it's a free $1, right? If no one's bidding anything, maybe you'll say, you waited for like a minute, you waited for 2 minutes, nobody bid anything. You say, okay, I'm willing to get that $1 for 1 cent, and you go and bid the 1 cent. Okay, this is logic, right? So somebody's just listening and being like, come on, it's a free $1. And they say, 1 cent. And then the person who's running the auction says, okay, I heard 1 cent as a bid. Is anyone willing to bid anything higher than 1 cent? And then everyone in the room is like, wait. So that person is going to get it for 1 cent. If I just bid higher than that 1 cent, then I'll get it. I'll be the top bid, right? So I should just bid 2 cents. So if I bid 2 cents, that person's going to, and they'll even pay for it, they're going to pay the 1 cent. I'll get for free, actually, I'll get the $1. Okay. And then the other person is like, wait. What do you mean? So you're bidding 2 cents, so you get the $1, and I have to pay 1 cent? What do you think that other person is going to do? Suppose that, you were the person who bid 1 cent, and somebody else bid 2 cents, which means that you are going to have to pay the 1 cent, and they'll get the 2 cents. What would you bid? $0.03, of course. So now here's the deal. You have two players, right? They've got two people. You've got player A, maybe Alice. Player B is Bob. Every game theory thing has these players, right? So at first, Alice was the one who said 1 cent, I'm going to get it for free, almost for free. Bob says, no, you're not. I'm going to pay 2 cents. I'm going to bid 2 cents. And what that means is that you're going to pay 1 cent. And then Alice says, no. I will pay 3 cents. And when I pay 3 cents, then you are going to end up, not pay 3 cents, I'll bid 3 cents. Then you are going to pay 2 cents, and I'll get the $1 for free. Bob says, no, you're not going anywhere with that. 4 cents. Okay, now this goes on for a while. We'll do this for a while. Actually, because of evenness and oddness, it goes on for a while. Maybe at some point someone gets lazy and just says, look, I'm just going to bid 50 cents or something. But however you do it, eventually, Bob is going to say 98 cents. 98 cents. And Alice says, no. 99 cents. And the reason Alice says 99 cents is because otherwise Alice had to pay. But now Alice says 99 cents, and then Bob is going to have to pay 98 cents, and Alice is going to get the $1. So what's Bob going to do? If you were Bob, what would you do? Right? Bob is in a situation where he has to pay 98 cents, and Alice is going to get the $1 for free. What would you do if you were Bob? $1, of course. Bob would say, okay, I will pay $1. I know that I started out thinking that I was going to get a good deal, but at this point, at least I won't lose any money. Maybe I can get the $1 for $1. What does Alice do? Alice says, wait, now Bob's gonna get it for free, and I'm gonna have to pay 99 cents for nothing. What's Alice gonna bid? Yeah, $1 for $1. That's already like not a great deal, but it's like it's worse to pay 98 cents and get nothing, right? And so now Alice is gonna say, in this situation, I would have to pay 99 cents and get nothing. So I should clearly bid $1.01. What's Bob gonna do? Alice is now winning, so Alice is in front. Alice is offering to pay $1.01, but Bob doesn't. I mean, Bob now has to pay the dollar, and Alice gets the dollar. Uh-oh. Wait a second. What's Bob gonna bid? Gotta keep going up. $1.02. Wait a second. Where does this go? It goes on forever. Well, does it really go on forever? It doesn't really go on forever because at some point someone's like, this is too much. Like, like suppose at some point it became like $20. It's like, it's pretty risky. Do you know why it's pretty risky? It's pretty risky because at some point, if you're going to bid and you don't actually have that much money, like suppose Alice in her pocket only has $20. This is now getting dangerous. You got to keep that in mind. Maybe Alice only has $20. Alice knows she only has $20. What would you do? If you know you only have $20, you better not let it get too high, because if Alice has only $20, at this stage, she doesn't know how much money Bob has. What if the situation is that Alice in her pocket has $20, but Bob in his pocket has $25? Do you know what would happen? If Bob has $25 in his pocket and Alice has $20 in her pocket, can Alice ever win? Alice can't. Yes, actually, Austin Shah said the organizer is getting money. And this is why you are not allowed to do this at school. Okay? Because the way this works, this is not a good game to play on your friends. Because like the organizer gives the $1 and gets in return whatever was like the second highest bid from the second person. But like you see over here, it's like somehow Alice is never going to win. Suppose Alice knows she's not going to win. Or maybe she's afraid because she actually only has $20 in her pocket. If she only has $20 in her pocket, it's like, what if at some point Bob just bids $20 and won? Then suddenly she has to pay her whole $20. Bob gets the dollar for free. And so this is why Alice might not keep going. So in reality, if you do the dollar auction, what usually happens is at some point it's getting close and people are like, I don't actually have that much money in my pocket. That is not cool. Yes, this is not cool, Paperboy. You're right. Don't do this at school. And I first learned about this in college. I was taking an economics class. Actually, the professor did this in the class. That's not very nice. But anyway, so somehow, not that it's not very nice. He didn't make anyone actually pay. But he actually, in the class, it was an economics class in college. And he said, hey, let's play this dollar auction. And let's just go and see like what happens. And these are like some pretty smart students, right? But unfortunately, once two people start playing, it goes da 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 da. And then suddenly, oh no. Bluff. I don't think you're supposed to be able to bluff here. Okay, but since you mentioned this thing about the dollar paradox, I'm not sure, or missing dollar paradox, I'm not sure if this is your missing dollar paradox. I might call this the missing $20 paradox or something like that. But it's something about dollars. Okay. Now, what else do we have here? Oh, Sophie Chang says, I'm from Canada. We don't use cents. Really? I actually didn't even know that. I didn't even know that. I've gone to Canada also. Again, before COVID-19, when I could travel around to give talks, I actually had a fun time going to Canada, to Toronto. I didn't realize you guys didn't use cents. I thought that the prices were all like something dot something something. But I wonder if what you're saying is that you don't have like pennies anymore. I'm actually not sure if that was your point. Oh, yes. Tiger Lee is in Canada too. Hello up there. Let's see. What else can we do? Okay, so I see Andy Wu has asked, which is harder, AMC path or math counts path? Oh, just do interesting problems. I mean, I don't think that you have to do one path or the other. Do both. These are all sources of good, interesting problems to play with. They're both good, so I recommend it. And they're slightly different types. The math counts ones can be very, very hard once you look at the national competition problems. And also the chapter level questions city level questions might be a bit more approachable. But yeah, I recommend you do both. And you'll have fun doing that. Those are both good paths. Hmm. Let's see. Oh, I see somebody who had asked, which website should I use for math? I recommend that every single person should go and check out different resources. There's no one best website for every single person. And I think that's a good thing. So use this time that you have to go and check out and try out different ways of learning from different people, different explanation styles, different levels of math, and you'll find what works the best for you. The important thing is to actually go and look and actually go and try. And I will tell you this because there is a difference. And it's not necessarily just a difference of better or worse. It's just different flavors. I mean, so if you never tried, you would never know. And this is also why in life, it's actually a good thing to be open-minded to trying different things. You might learn something. You might find out that you actually are quite good at something that you didn't know before. And that's not just about learning math. That's about learning anything. Other things. Skylar Schwer says Desmos. Desmos is pretty neat. Actually, the guy who made that, I believe. Well, I don't want to say this. I think he did some math contests before too. But he's a very interesting person. And I mean, a long time ago when I was a little bit more active in that sector of the online education, I actually had the chance to chat with him a few times about the kinds of work that they're doing. I think it's quite remarkable. It's also the idea of trying to help a lot of people. And so what they try to do is they try to make a graphing calculator that you can use that's free. Other things. Wow. I see that Kyle Hongran He has asked, what are the different classes of maths? And what maths do you prefer? I'm Kyle. Thanks, Professor Loh. So Kyle, nice to meet you. You call it maths, M-A-T-H-S. That means that you probably live in Australia or Canada or maybe even the United Kingdom. But if you live in the United Kingdom, it's probably getting close to bedtime. Now, maths is the same as mathematics, which those of us in America just call math. And if you ask me what kind of classes are there in math, I mean, there are a lot, but I really think that it's best to tie everything together the same way that we're trying to do all these daily live streams. It's like, yes, you can separate mathematics into different classes. On the other hand, if you do that, it sort of limits what you can use when you're trying to solve a question. So one way I've always enjoyed teaching is I've always enjoyed using questions. Like I make up my own questions. And I like to use questions that kind of tie together a lot of different concepts at the same time. And I will get maybe bored if I spend an entire year only doing algebra. So I will actually want to throw in lots of other kinds of mathematics to even show how, at the time that you're trying to figure out what an equation is that goes through two points, it might be related to something about finding out when the heavy rain starts, if you were here on our weekend live stream last time. So, all of these things, these are interesting, and they use lots of different concepts at the same time. So I recommend, if you ask that question, actually, if you just watch this live stream, you will see lots and lots of different types and different classes of mathematics all at the same time. And hopefully, they'll all blur together to you. And soon you'll think that, mathematics is really everything. Everything all at once. It's not bad. Okay. Yes, I see that somebody said she remembers that. So I assume that what she's referring to is maybe she's referring to the live stream that we did last weekend. And of course, I should probably remind people, there will be a live stream tomorrow. It will be at 8 o'clock p.m. Eastern time. And that one will be, slightly different in that I'll be taking all kinds of questions from different topics, not just math questions, or not just questions that are about explaining some concept. What else do we have here? So I see that there's a very, very interesting question that is by Aniket Sen. And I'm going to translate it into a way that doesn't use this sigma notation so that as many people can understand it as possible. What you wanted to know was what happens if I add up 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25, and I keep going. What is this? So this you could try to add up. And the question was, does it stop? Like, does it converge? Does it go towards a number and get closer and closer to the number so the number's distance from it is close to 0? And the answer is yes, it does. And I also see that there are some people here, like Anonymous Cheetah, who says it actually converges to pi squared divided by 6. This is really, really, really cool. The fact that when you add up 1 over the squares, and just add it up, you get a pi squared. Like, that's ridiculous. Why in the world would you ever have a pi squared? If you ever think about pi in formulas, you never square it, you know? Like a pi inside a formula is usually like pi r squared, not pi squared. Or even if you're doing the volume of a sphere, it's 4/3 pi r cubed, but the pi doesn't square. So this is really neat. Now, if you want to know why this is true, in fact, the nicest proof I know for why this is true uses something called Fourier analysis. I will not be able to talk about that here, but the nicest proof that I know uses Fourier analysis, which has something to do with sines and cosines. Now, this is where it's a little bit beyond the, not just a little bit, a lot beyond the topic of this particular live stream. But I'll just say, for this live stream, I'll just say this is a cool fact. And for anyone who actually understands Fourier analysis, one of the interview questions I ask people when I'm helping to interview for the Hertz Foundation Fellowship to go and find some super genius math and science and engineering people is I actually ask them if they can try to derive this. And I give some hints along the way to kind of hint at how you would use this Fourier analysis to go and try to come up with this. It's really neat. And through the hint that you use Fourier analysis, it's already a big hint. And if you know what that means, maybe you can figure this out. Okay. More questions. I see that some people, not some people, most people here are probably not like super experienced in this stuff. No problem, but you can see that thing, and that's cool. Okay, what else do we have? Oh, neat. Kyle Hong Ran He says, I'm in China. Oh, okay, because you said maths, M-A-T-H-S, so I assumed that you were in one of the other countries, like the British ones. But okay, wow. Hello in China. That's really neat. What time is it in China right now? You're in China? Are you sure? Isn't it like the middle of the night? Wow. Yeah, as far as I can tell in China, it should be something like really, really, really in the middle of the night. But thank you for your commitment to mathematics. Okay. I see some people here are in America, which, so am I. Hello. Okay. Yes, somebody said 4 a.m. Ancho says it's 4 a.m. in China. Wow. So there are some people here who are very, very, very committed to our live stream. That's all I can say. Which, well, that definitely makes me happy. I can see that we have 221 people here. And so the hope is that hopefully we'll get more people. To be honest, I've seen the numbers stay pretty stable at 220-ish. So my hope is that we are at least getting some new people, because maybe it's that, or actually, I don't know. Or is it that we have the same 220 people coming every single time? Who knows? Okay, well, hopefully we can keep getting more. Then we'll know at least that there's more people. Oh, that's very interesting. So Kirito Hey there asks, how many different iPhone passwords are possible? Please answer. Do you mean like the ones where you type a number in? If it's one where you type a number in, I don't know how many things you type to have a password unlock on iPhone, but if it's 6, I'm just making up 6. If it's 6 things and they're all 0 through 9, then you have, let's pretend there's 6 things. I don't know if it's 6 things or not, but whatever it is, the same principle will help figure it out. If you have 6 things that you can type in, if each one, 4 things. Oh, somebody said 4 or 6. Let's go with 6, yes. And then if there's 6 things you can type in, you can type in anything from 0 to 9 on the first one. So you have 10 choices for the first digit, and then 10 choices for the second digit, and then 10 choices for the third digit, 10 choices for the fourth digit, 10 choices for the fifth digit, 10 choices for the sixth digit, 10 to the power 6. Whoa. 10 to the power 6. So that's how many iPhone passwords you have. By the way, the reason why I think they chose to put 10 to the power 6, I'll tell you a good reason, okay? So somehow, what would happen? Like, how bad could it be if you just made it so that there were only 3 digits? Come on. Not even 3 digits. Like 2 digits, okay? What if we decided we didn't like this? Too many to remember, okay? Let's just do 2 digits. 2-digit passwords. How many different 2-digit passwords would there be? Yeah, I see some people answered my question for 3 digits. I want to make life easier. Only 2 digits now. 2-digit passwords. How many could there be? Only 100 options. Okay, so if there are only 100 options, is that a problem? Would it be a bad thing if there are only 100 options? Well, maybe it would be a bad thing, because maybe it would make it so it's very easy to guess. But is it that easy to guess? There's 100 things. And as you know, don't you know that with the iPhone or any of these devices, what happens if you try too many times? I'm actually not sure if this happens with iPhones, but maybe it happens with other devices. It's like if you try too many times on the same thing, what would happen? Do you know? Like usually I think a lot of these devices, if you try too many times, it's like, no, you get locked, right? So, like, come on. If there are 100 different possibilities, can you really try that many times? You can't. So actually this is not bad, right? It's good enough. Why are people doing 6 digits? Use the 2 digits. It's enough. Because as people are guessing, you can't guess 100. It would be good enough. Seems quite reasonable, right? Seems quite reasonable that we could just do 2 and just make it so that if you try 3 times and fail, you get locked. So that seems reasonable. Except that it's not. Here, let me tell you what's bad about using 2 digits. Even if you lock, what you could do is you could just run around your town, run around your room, or run around wherever you are, and just go and try different devices. And what I mean is, on the devices, you'll try until you're locked. But then you just go to a different device and try. And go into a different device and then try. And a different device and then try. And then basically you only have to go to like, I don't know, if you can try 3 times, you basically only have to go to like 34 different devices before, on average, you get into one of them. So what I'm showing is that this is actually the difference between only protecting one device and trying to protect all the devices. That's actually also game theory. This is how Apple and all of them have to think. It's that, yes, great, you can lock someone out after 3 tries, but does that bad person really care about getting into this particular device? Or do they just want to get into some device? If they want to get into some device, just go and go to all these different devices. And so that's a little bit of a lesson on if you're ever trying to make something that's secure, make sure you can think about it not just from the perspective of making it secure for one thing, but also make it secure for your entire system. Okay, what else can we have here? Wow, Ron Yoder, I see you have a question. Is that using the difference of squares to show p squared minus 1 is factorable by 24 if p is at least 5? You know what? I think we might be able to play with that. Let's try that, okay? So that's pretty cool. So what you're saying is, I'll call that number x. Oh, maybe x is weird. I'll call it n for a number. So n is a positive integer bigger or equal 5. And what Ron Yoder is saying is, let's figure out what is n squared minus 1. He says that it mysteriously is always divisible by 24. Is that true? Let's try. What if n squared minus 1, let's make a table. Okay, I'll cheat over here. N squared minus 1. If n equals 5, what is n squared minus 1? It is 25 minus 1, 24. What if n equals 6? What is 36 minus 1? 36 minus 1 is 35. Oh, wait. I think actually there's a reason why Ron Yoder used p. So p is probably meaning prime. Okay? So we're going to fix this because it's not true for this one right here. So we better switch to p for a prime. Okay? We're going to change the problem. P is not just a positive integer. P is a prime. We got lots of space, so let's write prime. Okay, so it's a prime, bigger or equal to 5. Let's see what happens. If p is 7, then p squared is 49 minus 1 is 48. That's neat. So far it still looks like it works. Whenever I ever get a question, I want to try it a bit. Next prime. What's the next prime after 7? Is it 9? No, it's not 9. It's 11. 11 squared is 121 minus 1 is 120. So far, so good. That's 24 times 5. What's 13? 13 squared. Oops. 13 squared is 169. So this would be 168. Okay, I think this looks like a legit pattern. Now I want to go and figure out why it's true. Now, if I look at this, whenever I'm trying to find out, what the question is to prove that it's always divisible by 24. If I want to do that, the first thing I'll do is I'll talk about divisibility. Sorry, these are called n's. They should be p's. I need to talk about divisibility. So let's see. If I have a number like prime squared minus 1, does anyone know a way, if I care a lot about divisibility, maybe I can try to factor this? Can anyone factorize p squared minus 1? That's not so bad. p squared minus 1. Yes, we're doing number theory now. So p squared minus 1 is what's called a difference of squares. And you can actually write p squared minus 1 as p plus 1 times p minus 1. And if you do this, p plus 1 times p minus 1, I wonder if we can use this to prove that the number is a multiple of 24. That's what we wanted. We wanted to have a multiple of 24. This is reminding me of like the number theory class that I was teaching. Multiple of 24. 24 is 3 times 8. Okay. So the first thing I need to do is I just need to show that this thing here is divisible by both 3 and 8, and then I'll be done. If I could just show that this is divisible by both 3 and 8, then it's divisible by 24. How do you know that p minus 1 times p plus 1 is divisible by 3? I can do each of those separately. Well, the way you can know this is that if you have a prime, what kind of remainders can the prime have when you divide it by 3? So the step 1 is to observe that every prime bigger or equal 5, now I see why you have bigger or equal 5, every prime bigger or equal 5 has, what are the possible remainders? Remainder, something or something, 1 or 2, thank you, 1 or 2 when you divide by 3. Of course, because when you divide by 3, your remainder is 0 or 1 or 2. And so therefore, if I'm a prime and if I'm bigger or equal 5, then for sure my remainder is not 0. Oh, look at this. If my remainder was 1 when I divide by 3, then this p minus 1 is divisible by 3. And I got it. What if my remainder is 2 when I divide by 3? If my remainder of this p is 2 when I divide by 3, then what is the remainder of p plus 1 when I divide by 3? 3, of course, which you can't have as a remainder when you divide by 3. It's 0. So the point is that if this prime has a remainder of 2 when you divide by 3, then when I add 1 to it, it's a multiple of 3. So this blue observation tells me it's always a multiple of 3. Now what remains is to try to explain why this is a multiple of 8. For that, here's what I'm going to say. These two numbers, are they odd or even? P minus 1 and p plus 1, if p is a prime, which is bigger or equal 5. What about p plus 1 and p minus 1, odd or even? What do you think? So they're both even. Okay, so they're both even. And if they're both even, then if I have an even number times an even number, surely that product is going to be a multiple of at least 4. But I want 8. So the point is that, yeah, thank you. I actually see that no name has said primes are odd. And so therefore plus 1 and minus 1 are even. So now this part's going to give me a factor of 2. That part's going to give me a factor of 2. 2 times 2 is 4. Not enough yet. But the good news is that actually you don't ever find two numbers that are 2 apart for which they are only factors of 2. The way to think of this is that if you look at numbers, let me just draw this out. If I have some numbers like 2, 4, 6, 8, 12, oh, what do you mean 12? 10, 12, 14, 16, I'm going to circle the multiples of 4. These are multiples of 4. Look, the multiples of 4 are every other. So, oh yeah, somebody asked, what if p is even? So p is a prime bigger or equal 5. That's why the bigger or equal 5 is important. That forces you to not be even. Okay? But now look at this. So if I have these two numbers differ by 2. They are two consecutive even numbers. They're even numbers that are right next to each other. And if I have even numbers right next to each other, there is no way to avoid a multiple of 4. Does everyone see that? No matter which two I take close together, I'll always get a multiple of 4 and a multiple of 2. I might even get more. I might get lucky. I might get a multiple of 8 also. But it's okay. I'll at least get a multiple of 4 next to a multiple of 2. I don't know in which order, but even and even, one of which is a multiple of 4. And so in that case, if one of them is a multiple of 4, bam, I have a multiple of 4 and a multiple of 2, because the other is even. 4 times 2 is 8. And that's why, if I take any prime number, which is bigger or equal 5, If I go and take the p squared minus 1, then this p squared minus 1 is always a multiple of 24. Okay, so I think, unfortunately, we've actually reached the end of our time for today. I really do think it's really interesting to have seen all of these questions. Certainly gave me a chance to go and try something. I actually didn't know this was going to work. But that's also why you saw at the beginning I wrote this down with n, and I immediately saw it's not true just with n. And then we quickly figured out you meant prime, and we figured out the whole thing. So I had some fun today as well. Thank you, Ron Yoder, for suggesting a question that I have to think about too. So that's going to be it for Friday. As a reminder, we've got something on Saturday. And if you have any friends, the Saturday one is also very interesting. And I encourage you to help us spread the word. Until then, have a very good day. Have a good rest of the afternoon, rest of the early morning, whatever the time may be where you are. And I'll see you next time.